All right, we're looking at section 9.4, problem number 32. And this problem asks us, we have a sum n equals 1 to infinity of this ratio of polynomials, rational function, p of n over q of n. The degree of p equals j, and the degree of q equals k. And it asks us to show a couple of different things. If this converges, if j is less than k minus 1 and diverges if j is greater than or equal to k minus 1. So I'm going to break this into three pieces. The two inequalities and the equality piece. So for the first case, I'm going to look at this inequality here. So if j is greater than k minus 1. What that tells us about the degrees of the numerator and denominator is that the degree of the numerator is greater than or equal to the degree of the denominator. So what I suggested in class is that you use some numbers. So let's let k equal 5. So this tells us that j is greater than 4. So we would have something like this. And to the, if j is greater than 4, it could be the fifth plus our other terms of our polynomial over 2n to the fifth. The degree of our denominator is 5 plus . Or the degree of our numerator could be larger. So n equals 1 to infinity here. Just another example. Say 3n to the 7th plus the rest of our terms over 2n to the fifth plus the rest of our polynomial. Well, in this case, we can use the nth term test. If we look at the limit of the nth term of any of these series, that limit is not going to be 0. Here the numerator is larger, so our limit is going to diverge. And when the degrees are equal, the limit is going to be the ratio of the leading coefficients here. So our limit is not 0. So by the nth term test, these will diverge. So you establish this first inequality. Now we can work on the equality. If j equals k minus 1. What that tells us about the numerator and denominator is the degree of the numerator is 1 less. The degree of the numerator is 1 less than the degree of the denominator. So if we use an example, we'll use the same numbers here. K equals 5 and j equals 4. So we would have something like this, n equals 1 to infinity of, say, 3n to the fourth plus the rest of our terms over 2n to the fifth plus dot dot dot. So this would be an example of what a polynomial, what our series in this form would look like. In this situation, I'm going to compare with a harmonic series. Because the relationship between the degrees of the numerator and denominator here are the same as they are here. One less in the numerator. So I'm going to use the limit comparison test here. And we're going to find the limit as n approaches infinity, p of n over q of n, divided by 1 over n, so I'm going to multiply by n. Well, when I multiply the numerator by n, that increases the degree of the numerator, so then the degree of the numerator and denominator are the same. And when I take that limit, I just get the ratio of the leading coefficients, which is finite and positive. So that's going to be greater than 0 and finite. So this would diverge by limit comparison. So when our degree of our numerator is 1 less, we limit comparison test with a harmonic series, and we show that that diverges. Now the third case, we want to show that this series converges if j is less than k minus 1. So if j is less than k minus 1, we're going to look at how the degrees of the numerator and denominator are related. The degree of the denominator is at least 2. More than the degree of the numerator. So for example, if we said that k equals 5, like we've done before, then j is less than 4. So the difference in the numerator and denominator is at least 2. So if we wrote out a series like this, we would have something like sum n equals 1 to infinity, and in our denominator we have 2n to the fifth, and in the numerator we would have 3n less than 4, so we would have third plus dot 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 plus dot dot dot. Or we could have something at least 2, so we could have something like this. So something in that form. Well, in this case, I'm going to compare with, I'm motivated by what we did last time. I'm going to compare with this series, sum equals n of n equals 1 to infinity of n to the j over n to the k. And if I rewrite that, that's a sum of n to the j minus k. And this is the sum. N equals 1 to infinity. J minus k is negative. So I can rewrite that as 1 over n to the k minus j. So k minus j will keep my exponent positive. So here, if k was 5 and j was 3, j minus k would be negative 2, k minus j would be 2. So this would be the sum, n equals 1 to infinity of n over 1 over n to the k minus j. And k minus j, with these conditions, is greater than 1. So it's 2 or more. It's like we talked about here. It's at least 2. So k minus j is at least 2 or more. So this series would be a convergent p-series. This is a convergent p-series. And we would look at the limit. We're going to use the limit comparison test. And as n approaches infinity, a Pn, Qn, just like we did with our harmonic series, into the k minus j, so multiplying by n to the k minus j. And the highest degree in the numerator, the highest degree in the numerator is going to be k, and that's going to be the same as the highest degree in the denominator. So in the example we used, the degree of the denominator is 5, k minus j is 2, and the degree of the numerator is 3. So we end up with a degree of 5 in the numerator for this limit also. So our degrees of our numerator and denominator are guaranteed to be the same when we do this comparison. Our limit is going to be the ratio of the leading coefficients of the polynomial that's left after we multiply this out, which is going to be finite and positive. So this is greater than 0 and finite. So we get convergent.